If you want to start recording, I think we're good to go. And so, Vincent, we're so delighted to have you here, and thank you.
And thank you for your kind work, kind words, Paul. Like has been a pleasure working with you, and I'm really glad I joined this project of building the PhysiCell ecosystem, and especially like PhysiBoSS and PhysiMess recently also, which is still very new, but I hope that it will gather some steam. So let me share the screen, and I think you should be seeing everything. Let me know when it's working. Yes, now you should see the screen.
Yes, we can see. Thank you.
Perfect. Okay, so welcome everyone. So today I'm going to talk to you about how to build multi-scale model with PhysiBoSS, and I will try to go step by step into explaining you with a concrete example how we do this. So first, I will have to introduce you a bit more about Boolean models that I didn't introduce in the previous session, to go deeper into the details of what we can do with a Boolean model, again with some specific example on self-head decision. Then I will explain to you the kind of Boolean models simulation framework that we are using inside PhysiBoSS, which is called MaBoSS. The main difference is that we are working with continuous time Boolean modeling and not just discrete time Boolean modeling, which are the usual ones. Then I will talk to you about PhysiBoSS and how it works and how we included MaBoSS inside PhysiCell. Then I will dive into the real examples so of this self-head decision model with the TNF model. Like this model is mainly controlled by two input nodes, one being TNF, which is this tumor necrosis factor, which will basically decide the fate of the cells being drugged with TNF. And finally, I will show you very quickly one new example, which is not related to the TNF, but which is a new cell cycle model for PhysiCell, which is using PhysiBoSS. Okay, so let's get started on Boolean models. So first, there are mainly two big frameworks used to represent signaling pathways. The first one is quantitative. Usually, it's using ordinary differential equations. So the values of your model inside your model of your variables can be any quantity. We are talking about real numbers. And also it uses continuous time, meaning that for any given time in your simulation, you can have accurate value for either your quantity of proteins or concentration of proteins, whatever you're modeling. The problem with this kind of framework is that they are very difficult to write. The math is not exactly easy, and you also have a lot of parameters to be able to really define your model. And also they are difficult to simulate, like to simulate large models. By large, we mean hundreds of components, hundreds of variables. It has a big computational cost. So it's one of the big disadvantages of this framework. And on the other side, we have qualitative framework, the most famous one being Boolean, where here it's a lot simpler because values are discrete. They are just 0 or 1. So you can see this as false or true, or absent or present, or inactive and active. So this kind of value are a simplification, but it's a simplification that we think works most of the time. Also, like in pure Boolean, you don't have a real notion of time. You just have a notion of sequence of events. So you know that this happened and then that happened, but you don't know how much time happened between these two events. You just know the sequence. But on the flip side, they are very easy to write. They are kind of close to natural language. So you can say, for example, that to activate protein B, you need protein A and protein C, and not protein D, for example. And one also big advantage of Boolean is that you can simulate very large models. Like we can simulate hundreds of nodes or thousands of nodes without any big computational cost. So let's take a very simple example of this interaction graph, where you see we have three variables inside our model. A will activate the node B, which is why we have this green arrow. and both A and B will inhibit the node C. So how do we write this into a Boolean? So A is very simple. It's what you call an input node, because as you can see, it doesn't receive any influence from the two other nodes. So it's just a node that we decide at the beginning of a simulation and won't move during the simulation. So we call that an input node. Then B will depend on the value of A, like it will be a direct dependency since it's a positive interaction. So if A is active and B is active, if A is inactive and B is inactive. And then for C, it will receive two influences of node A and B, which are negative influences, which are inhibition. So it will need A and B to be inactive. So we write it as not A and B. Then we need to define initial values for our model to start a simulation. So we'll say that A at first is active, B is inactive, and C is active. So here in this simulation graph, we can see the value of B and C. We don't plot A since A won't be changing value during the simulation. And you can see that we start with C equal to 1, so C active, B equal to 0, so B inactive. First thing we do is activate B because of the influence of A. And then once both A and B are active, C will become inactive. So this is a very simple example of Boolean model and Boolean simulation. So now let me introduce you the model we are going to work on today, which is a model of self-fed decision in response to depth receptor engagement. So this was a model published by Laurence Calzone and collaborators in 2010. Laurence Calzone is my boss, to make it very simple. He's working at Institut Curie and is a specialist of Boolean model and was one of the really initial team of PhysiBoSS, was there since the beginning. And so this is the model of TNF. So when we look at a model like this, at an interaction graph like this, we can see first that we have two nodes which are at the top, which are input nodes, so don't receive any influence, actually three. Also FAD doesn't receive any influence, so we have three input nodes. And then we have many intermediary nodes, which will receive influence of others and will also influence our nodes. And at the bottom, we have three nodes, which receives influence from other nodes, but won't influence others. So they are what we call the output nodes, or the phenotype nodes in this case. And here we have mainly three different kinds of phenotype that the cell will exhibit after the treatment with TNF or FASL or FAD. Either the cell survives, and it's actually a bit more than survival. We can say that she won't be dying, so it will be more like resistant. Then we have apoptosis, which will be the cell triggering apoptosis, one of the cell death. Then we have this non-ACD, which stands for non-apoptotic cell death, which in this case will represent necrosis. So the cell will activate another kind of cell death, which is called necrosis. And so basically, this is what the model will do. We just activate some input nodes, launch a simulation, and it will tell you if the cells is surviving, becoming resistant to a treatment, or dying of necrosis or apoptosis. So the first thing we do usually when we analyze simple discrete time Boolean models like this is we look at fixed points. Fixed points are one state of the network where once you reach it, you're stuck in it and you won't change anymore. And so here we have many different fixed points. All these columns are one fixed point. And so, for example, we can look at this first fixed point. We'll have ATP active, and that's it. All the other nodes will be inactive. And all these fixed points, like to decide in which fixed point you're going to end up at the end of your simulation, it will depend on input value. If you activate, for example, these FASL nodes, you will end up in this naive state, or naive means that you will have neither survival, apoptosis, nor necrosis. Or you can end up in survival or apoptosis or necrosis, depending on the other nodes which are active. One important aspect of this is that these simulations are stochastic. Even with the same initial value, sometimes you will have different fates. So you will reach different phenotype. This depends on the updates, what we call the update mode. And here we'll be using what is called asynchronous updates, meaning that we update one node at a time, and we simulate this until no node can be updated anymore. And so what's important in this stochasticity, it means that even with the same input values, we are able to reach multiple phenotypes, multiple cell fates. One important aspect also of what we do when we have this type of Boolean model is we can study mutants. We can study different treatments or different mutations. And this is something for which we can compare to what is happening in the real biology. So, for example, if we look at this NF capable deletion, so deletion means that we will force the node to be 0. We can see that this should induce apoptosis and necrosis when we submit them to TNF. And here we can see that indeed, when we simulate the model with this deletion and TNF, we will have a strong increase in necrosis and or apoptosis. And so basically we can study the properties of our model, also modifying this type of node activity inside our model. We can say, for example, that this cell line has a mutation into this protein. So when we simulate our model, we should obtain the same results as the experimental conditions. So now I'm going to present to you MaBoSS, which is some small modification of a classic Boolean formalism, so that it adds a notion of continuous time to Boolean modeling. I explained to you before that we don't have in pure Boolean a notion of continuous time. We just have a sequence of events. Now with MaBoSS, we can add continuous time. And so MaBoSS was developed originally at also. It was also Laurence Calzone and mainly also Gauthier Stoll who developed this. And the idea is that we wanted to have something more than Boolean models to include continuous time. And so MaBoSS stands for Markovian Boolean Stochastic Simulator. So as the name says, it's Boolean. It's also Markovian in the sense that we'll have a sequence of events, but between each event, we'll be able to know the time. We'll have a notion of physical time. And this allows us to handle different timescale process. For example, we know that transcriptions take a lot more time than phosphorylation. And inside our Boolean model, we'll be able to represent this. And so we believe that MaBoSS fills the gap between ODEs, which has a notion of time, but is very difficult to write, and Boolean modeling, which doesn't have by default a notion of time, but is easy to write. So we're basically trying to find the in between these two frameworks, and that's why MaBoSS was created. And so how does it work? The idea, like I told you, is that it's a Markovian process, so it's a sequence of events. So we simulate transition from one Boolean network state to another one. So, for example, we start with this very small Boolean network with this exact activity for each node. And then we compute the next transition and we update, for example, here, the value of the nodes, one at a time. And so we end up in a final state. And so here, the important part, which is added compared to Boolean network, is this part, is that for each transition, for each activation or inactivation of nodes, we will assign a transition rate. And this transition rate will be the one to decide how much time happened between these states and the other. Again, these transitions are stochastic, so we can have multiple trajectories. So what we do in practice is that we simulate many different times the model. Every time we reach a different state, or sometimes it will be the same state, but it can reach multiple states. And then from this set of all the trajectories that we simulated, we will compute mean trajectories. So you can see here you don't have any more 0 or 1. You have a probability of this node to be active at this time point. And so what we obtain basically are probabilities per state over time. And so how do we define exactly MaBoSS models? Basically, the main idea is to define activation and inactivation rates. So here, for example, we have a node A, which have a kinetic rate of 1 to be active. So it will have 1 time unit elapsed for its activation. And for its inactivation, it will be 0. So the node, once active, cannot become inactive. We can also see for node B, we have here a different construct where we first define a logical formula. So B depends on A. So this is where it's closer to a natural Boolean language. But here, so when we define the rates, we define it using this kind of ternary operator. So we say basically, if this logical formula is true, then we'll have an activation rate which will be defined by this parameter act B. Otherwise, if the logic formula is false, then the activation rate will be 0. And so this allows for a very complex case. We can have multiple rates for multiple states. We can build very complex formula using this. This is just a simple example. We can define parameters, which will be defined then in the simulation settings. So here, for example, act B is one parameter to define the activation rate of B. And this will be defined in the other file of MaBoSS model that I will show you just after. And we also have now other Boolean formats to be able to describe Boolean models. They are not exactly MaBoSS models, but they are closer to Boolean. These formats are SBML, Qual, and BNet. So we are compatible with other kind of formats in MaBoSS. And so now the other file that we have to define a MaBoSS model are what we call the simulation settings, which are embodied in a CFG file. So here we'll define really the settings of our simulation. So the initial states of the nodes at the beginning of our simulation. Here we define that A will be true, active, B will be false, inactive, C will be true, active. We are also able to define what we call internal or output variables, meaning that sometimes we don't want to look at the result of all the variables in our model because that would be too much information. So we are able to hide some nodes in our result. For example, we saw earlier that A won't move during the simulation. So we defined it as an internal variable so that it will be hidden from the result. Then we define our kinetic parameters. So here we define the activation rate of B and the activation rate of C also, which will be 10 times smaller than the activation rate of B. So the activation of C will be slower than the activation of B. And then we have like pure simulation settings. So how much time we want our simulation to go for. Sample count is the number of individual simulation which will be used to compute the probabilities. And then we have other settings like the kind of random number generator we want to use, or thread count, or if we want to have parallel simulation in parallel using multiple cores in your CPU. So here is one example of the result of a simulation in MaBoSS. So here we can see 3 states. We have 3 different possibilities. Either only the node B is active, either both the node B and the node C is active, or only the node C is active. So remember that we started our simulation with B inactive and C active. So at the beginning, we have probability 1, so 100%, to have only the node C active. Then, as time goes on in our simulation, we start activating the node B. And then we switch to have a majority of the probability to have both B and C active. And then, slowly over time, we'll have the node C turning to 0. So we will have mainly the node B active. And at the end of our simulation time, we will mainly have the node B active, and so C will be inactive. We can also look not only at states, but simply just at nodes. We just want to know, is the node B active or the node C active? So here we can see that at first, the node C is active and goes down, and the node B is inactive at first and goes up. But we lose some information looking at this. This is important to realize. But we don't know, for example, if at these states, if both B and C are active together, or in some probabilities of B being active on one side and C being active on the other side. So we lose some information, but you can still just look at nodes and not states. One important aspect also is that MaBoSS simulation are an approximation. We are not really simulating them until an infinite amount of time, until they stop simulating. Because we have a max time argument. So what we are looking at are the final state distribution, meaning at the end of our simulation time, which is different of a steady state, which will be after an infinite time of simulation. So here, for example, we can see that at the end of our simulation, we have 98.7% of the time, only B is active, and we still have 1% and something of the time where both B and C is active, meaning that we didn't simulate it long enough for all the C to become, for the probability of C being active to become 0. So let's go back to our select model, which is the one implemented for the Boolean, and let me show you what we can do with it when we use MaBoSS. So first, we look only at final time. So we can try to simulate different kind of treatments. Either we activate these TNF nodes or not. When we don't activate this node, when we don't put this value at 1 in the beginning of a simulation, what we obtain is a state called nil. Nil doesn't look obvious at first, but is actually very easy. It means that none of the output nodes are active. So we don't have no apoptosis, no necrosis, nor survival, nothing. This is what I refer to the naive state when I presented you the table of fixed points. And so in this case, when we don't put TNF, the cells don't become resistant, don't show survival because they haven't been used to TNF, they haven't been drugged with TNF, and they don't die either, they just stay quiescent. But then when we activate the node TNF at the beginning of our simulation, we can see that 90% of our cells exhibit apoptosis, 5.7% of our cells exhibit necrosis, and 4.2% are becoming resistant to the TNF treatment. So this is two different simulations, one with TNF inactive at first, one with TNF active at first, and you can see that they show different phenotypes and different distributions of phenotypes. We can also look at the state probability trajectory. So we can see that at first our cells are naive because we don't put any TNF treatment. So we don't have any phenotype active. Probability of nil is 100%. And then we activate the TNF treatment, and we can see that we mainly have one transition which will go to activation of apoptosis, which will reach a plateau very quickly of around 90%, like we saw earlier. And then we have a few cells which are red here, which are the necrosis, and a few cells which are purple, which are the resistant cell, which show survival. So we obtain basically the same distribution I showed just earlier. One very interesting aspect of this model is what happens when we activate TNF and then remove a treatment and then reactivating again and then remove it, which will be, for example, simulating a patient which takes some drugs every week and then the treatment stops and then he starts in the next week to have treatment again and then the treatment stops. And so here what we can see is that after this we can see the treatment duration in gray. So we can see that we reach the plateau after the end of the first treatment, then it's basically flatline here. And then at the second treatment, we can see more apoptosis, and so more cells dying in our tumor than we had after the first treatment. And this is because it's not completely obvious to see, but because we had some cells which are becoming resistant, which stop being resistant and go back to being naive cells, to being nil state. And then these new naive cells, when we activate the treatment again, will again divide into 90% apoptosis, 5% necrosis, 5% survival. So basically, by repeating the treatment, we can get rid of the resisting cells, the resistant cells. And so now let's see what happens when we put this model into PhysiBoSS. So first, let me remind you exactly what is PhysiBoSS. So the idea of PhysiBoSS is that we can put inside every of our cells, inside every of our agents, some Boolean simulation. This Boolean simulation will be able to decide the fate, what is going to happen for every cell, depending on the value of its microenvironment, depending, for example, in this specific case, if we are putting TNF inside the microenvironment around these specific cells. And so concretely, how does it work? Is that regularly doing our simulation at a period which is decided, which is called intracellularity, that we define inside our PhysiBoSS settings. We will, so every intracellularity, we will run an update where we look at the value of the environment of the cell. We see, for example, if the cell is in contact with ECM or with TNF. Then, according to the state, we will modify the input nodes of our Boolean model. Then we'll run a simulation, and then we look at the output nodes of our model to decide what's going to happen with the cells, and so to modify the behavior of the cell. One aspect which is very important to understand is that, contrary to pure MaBoSS, where MaBoSS will run many simulation and compute probabilities, here one cell will just run one single stochastic simulation. And so it won't have a probability at the end. It will just be either survival or apoptosis or necrosis or quiescence, meaning none of the phenotypes. And this will be stochastic, meaning that even with the same environmental condition, we can have heterogeneous response to a treatment. So how do we concretely define a PhysiBoSS model inside PhysiCell, inside the XML settings of PhysiCell? So inside our phenotype tag, we have this intracellular tag where we define the intracellular model. In this case, the type is a MaBoSS model for PhysiBoSS. What we then need to give to PhysiCell is the path to the BND and CFG file. Then also some settings of a simulation, such as the intracellularity. How often will this update of the intracellular model happen? Some other more complex settings that I will explain to you later, which such as time stochasticity or scaling. Then we can define initial values for our nodes, parameter values, just like in the CFG that I showed earlier, and also mapping, which mapping will be the mechanism which binds together some signals of PhysiCell, some value of inside PhysiCell to MaBoSS nodes, and also some values of nodes to PhysiCell behaviors. So let me give you again one small example of the mapping system. And so first we have the inputs, so linking PhysiCell signals to MaBoSS input nodes. So for example, suppose we want to have the node A being inhibited when we have oxygen around our cells. So what we'll do is that we'll write an input which binds together the PhysiCell name, which is a signal oxygen, to the intracellular name, which is an input node called A. And then we define that this action is an inhibition. And we say that A will become inactive when oxygen is above 10. And then we can define another threshold, which is optional, but the value on which once A is inactive, which value will be needed to turn back A active. And in this case, it will be the same threshold. So once oxygen goes below 10, A will become active again. Then the second part of the mapping are output nodes. So this time linking MaBoSS output nodes to PhysiCell behaviors. So suppose we want our apoptosis in PhysiCell to be controlled by the node C. So again, we create an output tag where we put the PhysiCell name apoptosis linked to the intracellular name C. This time it will be an activation. The node C will activate apoptosis. And then what we need to do actually is to set a rate for the apoptosis, because the behavior of apoptosis is controlled by its apoptosis rate. So here we'll say that when the node C is active, the apoptosis rate will be 5. And if C is inactive, the apoptosis rate will be 0, meaning that apoptosis will never happen. And here we can add another setting to our mapping, which is called smoothing, meaning that we don't want apoptosis rate to jump immediately from 0 to 5 when C becomes active. We want it to reach gradually 5. And in this case, we define smoothing as 5, meaning it will take 5 intracellular dt for the rate to reach the value of 5. And so PhysiBoSS was also able using the graphical interface of PhysiCell Studio. So when we go to cell types, you now have an intracellular tab where you can select what you want, Boolean intracellular, and you can modify and add all the settings that I showed you earlier in the XML definition. So the BND CFG files, the time step, and the scaling time stochasticity. You can add initial values, mutants, parameters, and also mapping inputs and outputs. We also added a specific visualization for PhysiBoSS inside the PhysiCell Studio. So when you load, when you run a PhysiBoSS simulation, you will have this new visualization option called PhysiBoSS, which will become active. So you can just select it, and then you will be able to select your cell type, and then for this cell type to select one node inside your Boolean model, so that you will be able to see where this node is active or inactive, in which cell is it active or inactive. Here, for example, we are plotting the value of the survival nodes inside our simulation, and we can see that survival is active in all the green cells and inactive in all the red cells. So now let's go back to this TNF example, and let's see how we put this inside PhysiBoSS. But first, this example was actually one of the few examples that Gael implemented inside her paper, which was the first paper of PhysiBoSS. And so what did Gael do with its model is simulate spheroids and try to see what was the effect of TNF on the size and the growth of a spheroid. So first, in the simple case where we don't have any TNF treatments, the size of population will keep increasing, and so the size of a spheroid will keep growing. But when we add TNF treatments, then we'll see that the size of population goes down because many of the cells will turn apoptotic. But after some points, this size of population will start going up again. Why? Because most of the cells will have the survival nodes active, meaning that the cells are becoming resistant to the TNF treatment. Gael also simulated other conditions, like what happened when we just have a short duration TNF and then we stopped. And here, since the cells are becoming resistant around these points, if you stop the TNF treatment, it won't have any effect since the cells are resistant to TNF. So either you put TNF or not, the cells will keep growing. Gael also tried to simulate a treatment of a larger dose of TNF, but in this case, since we are using a Boolean signaling network, we don't have a notion of amount. So we only have a notion of TNF present or not around the cell. So the dosage won't have any effect again. But one interesting point is that when you simulate pulsative treatment, so treatment which start and stop and start again and stops, then we can have cells which are not resistant anymore, and we can have a size of a tumor which is decreasing. So we will try to reproduce this behavior inside or with the new PhysiBoSS. So what we want to do here, what I want to show you, is how to develop a very simple model of TNF, simpler than what Gael did. It won't be 3D, it will be just 2D, because I wasn't able yet to implement the 3D support for PhysiCell Studio. So I just wanted to use PhysiCell Studio to show you this. So it will be 2D for now, but you can adapt it very quickly to become 3D if you want to. This time it will be using PhysiBoSS 2, so not the old version by Gael, the recent version with recent PhysiCell. And so it will be using the cell-fate model by Calzone et al. That I showed you earlier. And so at first, we start the a simple model of a 2D disk monolayer, so just a very small tumor in 2D which grows exponentially. And so to do this, we started basically by mixing up two different models which are present into PhysiCell. So first, the main template of PhysiCell, and then the project called PhysiBoSS cell line, which is the example of PhysiBoSS which is present into PhysiCell. So from the template, we took the latest version of the main.cpp and custom.cpp. One important part of this is that now with the mapping, we need the signals and behaviors dictionary being built. So we initialize them here. And then from the PhysiBoSS cell line, we took code which is specific for PhysiBoSS, which is still a bit difficult to do, but you just have to follow the example that we provide in PhysiBoSS cell line. So we do have a different makefile, because inside our PhysiCell simulation, we need to include the MaBoSS library for being able to integrate it into PhysiCell. And we also need, inside the main CPP, to export the values of our intracellular model into some text files. So we have added these two lines to be able to extract the states at any time of a simulation. Then what we did is we just, inside our PhysiCell Studio, define new initial conditions. So we started with a disk of 250 of diameters. We just have one cell type, and we choose an X field so that it's simple and easy. And so we saved it into our initial populations file. Then we added TNF to the microenvironment. So we defined a new substrate called TNF with some values for diffusion and decay. So this was mainly done by hand to be able to have a nice gradient of TNF arriving from the border of the cell into the core of the tumor. And as you can see, what we obtain is something where we have high concentration of TNF, so 10 here, and which diffuse gradually to the center, where we have not like some decay with the progression inside the tumor. Then what we needed to do once we add this TNF substrates is to define really the PhysiBoSS model per se, the Boolean model, adding the Boolean model to the PhysiCell simulation. So for this, we went to the cell types, and we went to the intracellular tab, and we choose a Boolean intracellular model. We then added the BND and CFG files of this cell-fate model. We choose sometimes steps, some scaling, sometimes stochasticity. This I will explain to you later, because this actually not the value are used, but are just example of values. And then we define the mapping. So very simple case. The TNF, which is the substrate of our environment, is now present into the signals. So we choose the signal TNF. We choose an activation, and then we choose the nodes inside our Boolean model called TNF. And then we found the good threshold to be able to activate it. So here, if a cell sends extracellular TNF to be more than 1, it will activate the node TNF. Otherwise, the node TNF will stay inactive. Then we added 2 outputs in our mapping. So for apoptosis and necrosis. So we choose the apoptosis node inside our Boolean model. We say that it's an activation. And here it's not signal, actually, it's a mistake in the interface. It should be behavior. So we choose the behavior apoptosis. So again, apoptosis is a rate. So we choose the value of a rate to be very high, meaning that once apoptosis turns on inside our model, immediately or close to immediately, the cells will turn apoptotic. And we do exactly the same thing for necrosis inside for the outputs. So basically, every time the node apoptosis or necrosis will turn active into the Boolean model, at the next simulation step, the cell will start the process of apoptosis or necrosis. And so now we need to choose the update periods of our Boolean model. And so the value of intracellularity. And this is actually a very important point. And here we basically have 2 different kinds of strategies. Either we choose a short intracellularity, meaning that we'll be able to have all the transient effects of our model. And so, for example, if a node just starts to be active and then becomes inactive again during the simulation, we will be able to integrate this into our PhysiBoSS simulation. But this needs a very well-curated model. You cannot have a node which appears and disappears if it's not biologically relevant. The other strategies, if you don't have a well-curated model, is to simulate a long intracellularity, to have a long update period, and so do long MaBoSS simulation. And so basically, it will be equivalent to wait for the steady state of a model. And so here, we won't have problems with the transient effect. But on the flip side, we won't have that much regular updates of our signaling pathways. So we have 2 different kinds of possibilities. And here, we have one issue with our self-fate model is that we have some transient activity which is not good inside our model. First, you can see that you have some big peak of survival at the beginning, which goes down later. And so this is not relevant biologically. Cells don't turn very quickly resistant and goes down later. But most importantly, we also have some phenotypes which are incoherent. For example, here we have this purple phenotype that you can barely see, but you can see better here, where we have cells activating both necrosis and apoptosis at the same time. And this doesn't make sense in biology. So we don't want to put this inside our PhysiBoSS simulation. So here, basically, we look at when do these problematic transient phenotype happen and when do they stop. And when they stop, we can conclude that at this time, we can say that the states which appear in the model are coherent with biology. And so we are simulating until this time. And so here, to avoid these problematic phenotypes, we choose to simulate our model for at least 24 hours, for exactly 24 hours. And so our intracellularity will be actually 24 hours, so 1,440 minutes. So then what happens when we choose this inside our simulation? So this is an example of the simulation of the model. So let's wait for it to go back to the beginning so that I can explain to you better. So we have a first tumor. We activate a TNF, and you see that most cells disappear very quickly together. Because of the TNF treatment, cells are dying. And then you have these green cells. Here I choose to show the resistant cells. Resistant cells start appearing, cells becoming resistant to the TNF, and then start growing exponentially. And so basically our tumor went down a bit, the size of the tumor, but then keeps growing because of these resistant cells. When we look at the size of population over time, we can see that we have our nil cells, our naive cells at the beginning. And then at the first update of our model, after 1000, at the second update, actually, there is one first update where TNF is not here yet. And then at the second update, cells fill the TNF, start killing most of the cells, but then some cells in red become resistant. And then this population of resistant cells will increase until becoming the majority of a tumor. You see that you have some cells which are necrotic also, which becomes an important part of a tumor. But here, what is kind of problematic, because it's not exactly, again, biologically coherent, is that all of the cells activate just at one time and just die, all of them together. And this is not what's happening in real time, in real biology, in real life. So here, what's happening, as I said, is that you have mainly two updates happening in our model. First, at time 0, where all the simulation starts. We don't have TNF yet, and all the cells update. And then at times 1 day, we have most of the cells again being updated. And that's at this time that most of the cells are dying. You might ask, what are these cells which are also updating between these two peaks? These are the new cells being born. And so every time a cell is born from division, it will also update its intracellular model. And so this is what happens when we have these settings time stochasticity set to 0. We don't have any stochasticity in the time of update, but that's something that we can add. And basically the idea is that, okay, cells will start the simulation and run once already a Boolean model. But then for the second update, all the cell won't happen, all the updates won't happen exactly at the same time. There will be some fluctuation, some cell-to-cell variability on which, at what time the cell will update. And so here is an example where when you put time stochasticity equal to 0.2, we have the first update, like I said, at the beginning of the simulation, but then we have the second update, which is this distribution here. So some cells will update before, some cells will update after, but it's centered around this 1 day update time. And so here, when we put these settings, we can see that the cells don't disappearing all at once. So it's more similar to what's happening in a real experiment. But in the end, you will still get the same tumor becoming resistant to TNF, the same cells becoming resistant to TNF, and so the cells coming back to grow, to the tumor back to growing, but this time resistant to the treatment. And when you look at the time course, you see basically the same thing as before. We have our initial population of naive cells, but this time they won't, they're not killed all at the same time. There is a gradual descent in the size of the tumor and a gradual increase in the necrotic and apoptotic cells. And so now what we want to do with our PhysiBoSS simulation is try to reproduce this example that we showed here on the MaBoSS model. This idea that by having pulses of treatment and not just one continuous treatment, we are able to kill more cells inside our tumor and to have the size of the tumor actually going down in time. So for this, I cheated a bit and I didn't use only the graphical interface because I needed to add some code to do the treatment of TNF. So this is still something which is not perfect, but I have some hope that there is a project called PhysiPKPD, which was also born as a project of a PhysiCell workshop that at some point we need also to include as an officially supported add-on. And this will allow us to do basically the same thing, to simulate treatments which can be periodic, which can be pulses. But for now, so I added this code to be able to define that I want a treatment with this substrate and which will be with this specific periods and a specific treatment duration. And so what happened when we create these pulses of TNF now into our Boolean models is that we can see we have a first death, then population goes back to become naive, a second death, then population goes back to become naive, and then a third activation. And so you can see that we don't have anymore this population of resistant cells, because resistant cells are turning back to become naive thanks to the stop in our treatment. And when we look at the time lapse of our simulation, we can see that we have our naive cell at first. We have a big quantity of cells dying and cells becoming apoptotic, becoming necrotic here. And then when we stop the treatment here, I should have put the green bars, I didn't, I'm sorry, but here the treatment of TNF stops. And so the tumor starts growing again. But more importantly, the cells which are resistant cells, which are here in red, started increasing during the treatment, but now they start to go down again. And most of the cells which are growing now are appearing are naive cells again. And so when the second wave of treatment starts here, we again go down to a lower value than the previous one. And when you make the sum of the size of a tumor, the sum of all the type of cells, you can see that you have a gradual descent. Now, the other thing that Gael did also in our model that we can do easily into PhysiBoSS is to add a necrotic core inside our tumor. The idea here is that the cells are sometimes dependent on the presence of oxygen around them to be able to not die of necrosis. And so if you have this type of tumor, you will have a layer at the periphery of a tumor of cells which are alive and proliferating. But all this layer around the cells, around the tumor, will consume the oxygen. And so there won't be any more oxygen to reach the center of the tumor. So the center of the tumor will be composed of mostly necrotic cells because of this lack of oxygen. So this is something that can try to reproduce with PhysiBoSS. So here the basic idea is that we need first to modify our Boolean model because we don't have a notion of oxygen inside our Boolean model. So we just add a node oxygen. It will be an input node, so it doesn't need any activation or inactivation. We can just decide the value either as an input node or in PhysiBoSS, depending on the environment using mapping. And then we put this oxygen as a component of our nodes of phenotype. So to be able to activate the node non-ACD, which again is necrosis, we need either to have a lack of ATP, which was the case before, or to have a lack of oxygen, to not have any oxygen. And in order to not have a mixed phenotype, we need to say now that apoptosis will need oxygen active on top of having caspase-free active also. Because otherwise, if we lack oxygen, we could have both apoptosis and necrosis at the same time. And we need also to say the same thing for survival. So survival will need oxygen in order for the cell to become resistant. Then in our CFG files, we can define the initial state of oxygen. So at first, cells have oxygen and are proliferating normally. Then what we need to do inside our PhysiCell simulation is to add this new substrate called oxygen. We define some diffusion and decay rates and initial condition, which was again kind of fitted manually by myself to be able to have something beautiful to show, but which needs to be fitted according to biological value in real life. Then inside our mapping now, we go back to our cell types and intracellular definition, and we add a new input mapping to say that the oxygen will control the activation of a node oxygen inside our PhysiBoSS simulation, inside our Boolean model. And so we define the threshold above which the node oxygen is active or inactive. And once we have this, we can just run our simulation, and we can see here I'm coloring in green the cells which are necrotic. And so we can see that as the tumor grows, we just have this layer of cells in red which have access to the oxygen, so are able to grow exponentially as usual with a TNF treatment. But the core of the tumor will turn necrotic. So this was just a simple example of what you can do more when you improve your Boolean model and you can create new behaviors like this. And I won't go into the detail of what's happening when you add TNF treatment to this kind of tumor with necrotic core, but this is also something that Gael developed in her paper. And finally, one last thing that Gael also did inside our simulations is to simulate heterogeneity in the composition of a tumor. So tumors, most of the time, are not just one single type of cell, or can show some specific differences between cells inside the tumor. And so here, for example, we'll be studying one specific mutant inside our tumor, which is an IKK and CFLIC, which are two proteins inside our Boolean model. And what's happening when we force their activation? And this is something which was showed in the table of steady state earlier, but when you do this to this TNF model, to this cell fate model, the cells will become naturally resistant to the TNF. They don't need to acquire resistance like I showed you earlier, like they won't care at all about TNF like by default. So then how do we define this new mutant population? We just go to our cell types definition and we can just copy our default cell type and create from it a mutant cell type. So it's exactly the same settings for the cell type, except that in this mutant, we'll add two mutations inside our model, which will force the node IKK to be always one, whatever happens. And same thing for CFLIC, will force it to be equal to one, whatever happens. Once we have our two cell types defined, what we need to do is to have a simulation where both cell types are present. So for this, we just went to the initial conditions. We again decided to create a disk of radius 250, but this time we choose random fill, where we said that at first we have our default population, which will be, I think it was 500 and something, and then our mutant, which will be 267 cells. This time we choose random fill because we need to decide the number of cells for each cell type. So basically here in this simulation, we have gray cells, which are the default cells, non-mutants. There is 500 and something of them. And we have these red cells, which are the mutant, and there is 267 of them. And so we save this into our cell mutants. And then inside our configuration basics, we choose the initial state to depend on this file. And so what's happening when we simulate this, it's kind of evident is that even with treatment of TNF, the tumor will be growing. Why? Because all the gray cells, which are the default cell population, this one will die from TNF treatment, from pulses of TNF treatments, like I showed you earlier. But all the green cells will just keep growing exponentially, even with a TNF treatment. They won't care about TNF. So basically, our tumor will keep growing slightly slower because at first you still have some cells which are not mutants, but then we really grow as if there was no TNF. And so we have at first a population which was mainly default cells, non-mutant, but very quickly the tumor will become composed only of mutant cells, despite the pulses of treatments of TNF. So this was what I wanted to show you as an example of how we build treatments, we build a model with PhysiBoSS. Now I want to show you something which is very new, which was developed by Marco Ruscone, our PhD student at Curie, and is something we wanted to do for a long time. Initially in PhysiCell, we have some cell cycles which are simple case where we have just decide how many states, how many phases we want inside our cell cycle model, with some specific rates of transition between each phase. But we wanted to have a real, meaning a real signaling pathways controlling the cell cycle of PhysiCell. So for this, we decided to create a new PhysiBoSS model with, as a Boolean model, a model developed by CZEC and collaborators, which is this model of signaling, which controls both the cell cycle and actually also apoptosis, and to plug it inside the control of a PhysiCell cell cycle model. So here you can see that we have the classic behavior that is shown in biology of the transition of the different cyclins inside our model to represent the different, the successive activation of a different phase of a cell cycle. So first, what we need to do is we needed to clean it up a bit and to really have 3 new nodes which define really the transition of our cell cycle model in PhysiCell. So we need to have something which defines the entry in G0, G1, or the entry in the S phase, or the entry in the G2M phases. And also being sure that we don't have both G0, G1, and S entry activated at the same time, for example. So we wrote these specific formulas to be able to achieve this. And this is an example of a reduced state transition graph, which shows the path of the simulation. So we start from cells being mainly naive cells, so they are not cycling yet. Then we enter in G0, G1. Like the darker the shade of blue, the most likely this transition is. So usually we will activate G0, G1, then activate S entry, which will then deactivate G0, G1, then activate G2M entry, which will deactivate S, and then go back to nil. And so we will be cycling like this. You can see that you still have some probability of doing something wrong, which is a limitation in the model. It's a limitation of the transient behavior, but it's a limitation that we have to live with or find a way to improve this cell cycle by CZEC and collaborators. And then what we need to do to PhysiCell is, so we take a template of PhysiCell with just some small population of cells, and we add this Boolean network into the intracellular parts. And then we choose, again, type step scaling stochasticity. Here, one important aspect is that, as you can see, we don't have really fixed points because we want to have all the transient effects. Remember what I told you earlier about the short versus long intracellularity? Here, we want the short, the intracellularity, because we want to see first G0, G1 activating, then S, then G2M, and then these things starting again and again and again. We don't want to wait for the model to stop updating, because in this specific case, it won't stop updating. So we choose a short time step in this case. And then we defined our output mapping to say that the cell cycle entry will actually be controlled by the node S entry. Then the exit from cell cycle phase 1 will be controlled by the G2M entry. I think there might be some error in the names here, but trust me, it works mostly. And then after all the phases of the cell cycle are defined, we choose also the apoptosis as an output, because apoptosis is also controlled by this, this model of CZEC. And we can say that when we have caspase-free active, cells turn apoptotic. And here you can see that we choose very high rates for this mapping, meaning that every time the node S will turn active, the cells will activate this transition, this behavior. One thing we also did, and I also shouldn't forget this, is that we adjusted the MaBoSS kinetic rates of this specific Cizek et al. Model so that we are able to reproduce the same speeds as the PhysiCell default cell cycle model, which is not the default, is the flow cytometry cell cycle model. And so here you can compare on the left PhysiCell normal cell cycle, and on the right PhysiBoSS Cizek cell cycle. And you can see that we have more or less the same speeds of growth of this population. And you can see that we have, you can look at the different phases for each phase, if they are in S, G0, G1, G2M. And also you can have the red cells which are apoptotic on the PhysiBoSS model. And now that we have this type of model, what we can do also is to introduce some mutants, because, for example, in many types of tumors, you will have mutants affecting the cell cycle, and we wanted to be able to reproduce this inside PhysiCell. And that's one of the things we can do easily with this Boolean control cell cycle. For example, we know that if we do a knockout of PLK1, cells will become stopped at the G2M transition, and basically cells will accumulate at this G2M phase. And this is exactly what we are seeing here. When we activate this mutant, this KO, this knockout, and this can be done with drugs, for example, we can stop the proliferation because all the cells will become stuck in this G2 phase and won't be able to activate mitosis. Then we also have some mutants which will modify the proliferation rate of our tumor. We can see, for example, this inhibition of FOXO3 will be slowed down compared to the default and compared to this double mutant of PI3K and P110, where the proliferation rate will be higher than normal. And so this was the two examples I wanted to show you of PhysiBoSS, and I hope now you understand a bit more what is PhysiBoSS and how you can use it. And so these models are now available on the SysBioCurie / PhysiBoSS v2. Actually, the link is wrong, but I will post it soon in the chat. And they are on the and the name of the project is called PhysiBoSS tutorial. So the conclusion of this is that this is just two small examples, some actually very easy example. We can have more complex examples. Parameterization is not easy. This is something I barely went into the detail of why we choose this value or this value, and all these parameters should be fitted actually according to the biology. So these for now are just kind of toy models. And I learned many things while preparing this example. This was true last year and is still true this year, and I will have more bug fixes to submit later. And these two models and others will be part of a paper that we are preparing together with Marco Rustone, my PhD students, which will be a PhysiBoSS tutorial explaining you exactly the steps we went through to be able to develop this model and what are the important points that you need to take care of. And so in conclusion, PhysiBoSS started as a fork of PhysiCell even before it was published, showing the importance of open source software development in science. So we were able to really quickly use PhysiCell. It took a lot of time to be able to really merge the two together, but now 6 years later, PhysiBoSS is tightly included into the PhysiCell ecosystem, and we are making regular updates of PhysiBoSS and helping Paul to update PhysiCell whenever we can. Writing model is getting a lot easier. Like at the beginning of PhysiBoSS, when Gael created it, it was just C++ code. Now I showed you that we still have a bit of C++ code, but most of the thing can be done just with the graphical interface. And so now feel free to ask me any questions, suggestions, issues. This is the official repository of PhysiBoSS, which is not completely up to date, but I need to finish this soon. And if you have any question, I'm available at this vincent.noel@curie.fr. And so we'll finish by acknowledging all the worked PhysiBoSS and MaBoSS. So at Institut Curie, people from the original MaBoSS and now PhysiBoSS. Marco Ruscone is a PhD student who developed the cell cycle and other models of PhysiBoSS, including a brand new cancer invasion model. Then I need to thank also all the people from Barcelona Supercomputing Center, which are we are developing PhysiBoSS together and by hand, and are really instrumental in the new update of PhysiBoSS to be able to reintroduce it into modern PhysiCell. And finally, also the people from Indiana University, Paul and Randy, who are always supportive and here to help us. Furkan, which was actually the one who helped me and who explained to me what he was doing with the mapping, which inspired me to do the mapping into PhysiBoSS. And of course, Gael for starting all of this effort of PhysiBoSS. And then I need to thank all our funding partners, both for PhysiCell and for PhysiBoSS. And with that, I will take your questions, if you have any.
Thank you very much, Vincent. So actually there are a couple of questions in the chat box. Do you want me to read them?
No, I can open it.
Okay.
Is a cycle attractor of X.2? No, I don't know if it was explained later, I guess, but yeah, fixed point is a point where none of the nodes get modified ever again. So a cycle attractor, you will have a sequence of node activation and inhibition and inactivation, which will be periodic, but it's a different kind of attractor. And what is the structure of the output data for PhysiBoSS? This is something that I might want to revisit after some points. But for now, what I have is just a CSV file, which has for every cell one line with the ID of the cell and the state of the Boolean network. So they are just CSV files which are present in the output directory. And this is something where we might want to coordinate together with other intracellular implementation to have something which is better and which is more consistent. There should be 2 to the power of 4, 16 different logical gates in BND. Can you use all of them? Yes, you can define. Yes, it's true that I showed a kind of direct link between the interaction graph, so the green and red arrows, and the Boolean formulas. Actually, it's not that simple, because you can have, for example, in the case I showed at the very beginning, I didn't show the, say the truth, is that here, for example, C, I say that you need this formula. You need A and B to be inactive in order to activate C. But it could be A or B. Like this is not specific enough to define the exact formula. So you can have many variations if you want to translate an interaction graph like this into a Boolean network. And this is something that we are actually working on very deeply. So we usually take some default formula, meaning that we need all the activators and at least one inhibitor. And then we are refining this formula by hand to be able to reproduce the experiment. But we also have some framework, for example, a framework called PhysiBoSS, to be able to give actual biological data, an interaction graph like this, and ask the framework which are the Boolean formulas which are compatible with both this graph and the data. So this is still a point of research and which is still a very tricky part that we need to work more on. PhysiBoSS is not linked to the PhysiCell phenotype time step. So as I said, PhysiBoSS has its own intracellular time step, as I think most intracellular implementation have. And this is something that you can define in PhysiBoSS. For every model, you can have its own intracellular DT. On slide 45 and 46. How did I track this exactly? So this, I just modified the C++ code to be able to store the update time for every cell. We don't have something exact. We don't have anything in the output which stores this. So this I had to cheat a bit and do this graph by hand to be able to show you that the update time for each cell in the simulation. Remember number 2, Capgal simulated the patient with some tactable drug and sometimes forget to take the drugs, and because of that double dose, or because of that skips. Yes, and there was something in another talk where skipping dose was better, I guess. So yeah, this is something which can also be studied in the same way that I showed you, like this idea of interrupting or forgetting treatment. And thanks a lot, John. How are the relevant nodes from Boolean network mapped to the phenotype of the agents? The details, Hoffman, the details are, I didn't present them, but the idea is that you will have, for the output, you need to translate a Boolean value inside to a continuous value, a continuous rate. So you will have, if you don't define any smoothing, you will just have, when the node becomes active, then the value of a rate jumps to 5. If you define some smoothing, it will be some kind of sigmoid to define the activation rates in time. So for example, in the example I showed, it needed 5 time points to reach the max value. And so it will actually follow a sigmoid to be able to reach the max value. And this sigmoid will be like, value will be 99% after 5 dt. This is something that I promise I will give good example in the tutorial paper we are preparing, and there will be some parts probably in the supplementary with all the details you want about how we do this step function. But yeah, it's actually using one of the ill response function that Paul coded, and we are just using it to be able to compute this this gradual increase. And thanks a lot, Elmar. Okay, more questions? And if you have any more questions, also really feel free to ask them either in the Slack. I'm present in the PhysiCell Slack most of the time, or into at Vincent Noel at Curie.fr. Feel free to ask any question which comes to you later during the day or during the workshop. And if you want any help during the workshop also to include Boolean models, I will be available.
All right. Thank you very much, Vincent, for this great talk.
My pleasure.
Yeah. So Paul, would you like to do the logistic for the rest of? I think you did, but yeah.
Well, I think, let's make sure that we're through all the questions before we wrap up. We can always adjust our schedule. And also, let's thank Vincent for presenting this, and the advances in making this accessible and usable are just phenomenal. And so it's just really impressive to see. So everyone, thank you, and please join me in thanking Vincent for this talk.
And thanks a lot for attending.
Yeah, I think let's go ahead and stop the recording if you haven't already.